All right, today we're going on a journey. We're going to follow the invisible, incredible path electricity takes, starting at a massive power plant and ending up, well, right in the palm of your hand.
I mean, think about it. You plug in your phone every single day, probably without a second thought. But behind that simple, everyday action, there is a massive, incredibly complex system at work. So let's dive in and trace that journey, which, believe it or not, all starts with a huge choice that was made more than 100 years ago. So our journey really begins with the very nature of electricity itself. You see, our entire power grid, the whole thing, is built on a choice that was made between two competing types of electrical current. On one side, you've got direct current, or DC. Just think of it like water flowing through a hose. It goes in one steady, straight direction. Super simple. But on the other side, you have alternating current, or AC. Now this one's a little weirder. The flow actually reverses direction back and forth over and over again. It might sound kind of counterintuitive, but that one little difference, it turned out to be an absolute game changer for powering the entire world. So why did AC win what they called the War of the Currents? Well, it really boiled down to three crucial advantages. First, and this is the big one, you can easily change the voltage of AC power using transformers. This is absolutely vital for sending power super efficiently over long distances. Second, AC motors are just better. They're more robust, they're cheaper to build. And third, all the switchgear, the equipment that controls and protects the grid, is just a lot simpler and more reliable for AC systems. In this elegant sine wave, this is what alternating actually looks like. The voltage isn't a flat, constant line. It smoothly rises to a peak, falls back down, reverses direction, hits a peak on the other side, and does this whole dance over and over. This constant change is the secret sauce. It's what allows transformers to work their magic. Okay, so we've established we have powerful AC electricity coming from our walls. But here's the catch. Pretty much all of our modern gadgets, your laptop, your phone, you name it, they don't run on AC. They actually need low-voltage DC. So how do we bridge that gap? Well, the answer lies in an amazing field called power electronics. Power electronics is basically the universal translator for electricity. It takes that raw power from the grid and converts it into the exact, precise form that our devices need to function. It is the quiet, unsung hero inside every single charger you've ever owned. And this isn't just one simple thing. Look at this chart. Power electronics is this amazing intersection of so many different disciplines. You've got power systems, circuit theory, solid-state physics. They're all working together to manage and convert electrical energy with just incredible precision. So the first and most common job for power electronics is exactly what you see here, converting AC to DC. Every single time you plug your phone into the wall, a tiny converter inside that power break is taking the high-voltage AC and turning it into the low-voltage DC that your battery can safely handle. But the story doesn't stop there. Once that power is inside your device, it often needs to be converted again. A DC to DC converter takes that initial DC voltage and changes it, stepping it up or down to power all the different little components inside your phone, because they all need slightly different amounts of juice. And just to complete the circle, we can even go in the other direction. A DC to AC converter, which we usually call an inverter, can take power from a DC source, like a car battery, and turn it back into AC. This is exactly what's happening inside an uninterruptible power supply, or UPS, that can keep your computer running during a blackout. Okay, so our device is powered up, it's charged. Now what do? We use that power to connect, to communicate. And this is where the flow of electricity enables a completely different kind of flow, the flow of information. Now, this diagram might look a little technical, but I promise you, it's the fundamental blueprint for any kind of communication. You have a source with a message, a transmitter to send it, a channel it travels through, a receiver to catch it, and a final destination. This simple model applies to absolutely everything, from a phone call to a simple text message. So let's see that principle in action. On the left, you've got our basic model. And on the right, that's how it scales up to become the cellular network. Yeah, it looks a whole lot more complex, but the core ideas are exactly the same. Your phone is the transmitter, the air itself is the channel, and that cell tower is the very first step in a massive receiving and routing system. So let's break down what happens when you make a call. First, your phone sends a signal to the nearest cell tower. That tower then passes the signal along to something called a base station controller, which is kind of like a manager for a whole group of towers. And finally, that controller sends it to the switching center. You can think of this as the network's brain. It's what routes your call to its final destination, whether that's across the street or all the way across the globe.
We have covered a lot of ground, from the massive power grid all the way down to tiny little signals. But there is one final and absolutely crucial piece of this invisible network that we need to talk about, and that is safety. This is where something called earthing, or grounding, comes into play. It's a really simple but absolutely vital safety concept. Basically, the metal casing of an appliance is connected by a wire directly to the earth. This gives any dangerous, stray electricity a safe, easy path to follow, a path that isn't through your body.
And of course, it's part of a broader set of safety rules we should all know and remember. Use insulated tools. Don't overload your sockets. Keep water far, far away from electricity. And of course, never, ever touch an exposed live wire. These simple practices work together with systems like earthing to prevent accidents.
Now, this is a perfect example of why earthing is literally a lifesaver. Imagine a wire comes loose inside this metal iron, and it touches the metal casing. The whole thing becomes live with electricity. If you touch it, you're going to get a severe shock. But now look at the iron on the right, the one with earthing. Same problem, a wire comes loose, but this time, that dangerous current has a safe path straight to the ground, instantly tripping a circuit breaker and preventing any harm to you whatsoever. So, from the huge choice of current that powers our grid, to the tiny electronics that tame it, to the networks that power our conversations, and finally, to the safety systems that protect us, it is an extraordinary, invisible journey. So the next time you charge your phone, what part of it will you think about?